Okay, so Assalamu alaikum everyone, and welcome to the differentiation masterclass. In this masterclass, we will be covering the entire A2 level differentiation from scratch. We will be first revising the AS models and then eventually proceeding to A2 models. So in short, we will be covering everything you need to know for your exam, every differentiation model you need to know for your exam. So if you watch this entire video, you are ready to the differentiation chapter is ready for you. Okay, so this video will consist of around 27 models. All right, 27 models of differentiation. Right. So if you complete those, learn them learn those, you are ready for differentiation, and then you can proceed to integration. All right. So without any further ado, let's start off. Okay. So, so differentiation, as we learned, differentiation is referred to referred to as gradient function. Gradient function because because it helps in in identifying the gradient of the curve at different points of the curve. All right. It is denoted by it is denoted by dy upon dx or f dash x or simply y dash. All right. So by the way, you have to copy these notes alongside me. So with that, before your exam, you can just simply revise. All right. It is really important to copy them down as it is. Okay. So it is denoted by dy over dx or f dash x or y dash. The difference between the difference between gradient function and gradient is the that fact that the gradient is a fixed value is a fixed value, whereas the function gradient function is equation of the gradient is equation of the gradient. All right, so this is simply what differentiation is. Now, in order to apply differentiation, we have to apply certain models. All right, so starting off with our first model, and these models are 27. All right, 27 models. So let's start off with our very first model. So model number one. Model number one. let's say y is equal to x power n. So dy over dx would be dy over dx would be n comes down n x power n minus 1, right? This is what dy over dx would be. So let's say, for example, we have y is equal to x3. So dy over dx would be 3x squared. All right. Let's say y is x power 5. So dy over dx would be 5x4. All right. And let's say y is equal to x under root x. This is the same thing as x power 1 upon 2. All right. So dy over dx would be half x 1 upon 2 minus 1, which is minus 1 upon 2. And dy over dx be 1 upon 2 under root x if we simplify it. All right. So this is our model 1, which we have already studied in AS. All right. Now 26 models to go. So model number 2. Model number 2. All right. So model number 2 is simply an extension of the first model. All right. Let's say y is equal to ax power n. All right. So dy over dx would be a n x n minus 1. All right. So let's do a couple of examples. Let's say y is equal to 5x power 9. All right. So dy over dx would be 5 nines are 45 and x power 8. All right. Similarly, let's say y is equal to 12x cubed. So dy over dx would be 12 threes are 36 and x n minus 1, 2. All right. Similarly, y is equal to 4 under root of x. So we can write this as y is equal to 4x power 1 upon 2. So dy over dx would be 4 into half x 1 upon 2 minus 1 upon minus 1, sorry, minus, which would give us minus 1 upon 2. If we simplify this, we get dy over dx is 2 upon under root of x. All right. So this was model 2 for you. Moving forward to model 3. Model number 3. All right. Y is equal to ax. So dy over dx would simply be a. All right. When y is equal to ax, dy over dx is what? A. So let's say y is equal to 5x. Dy over dx would simply be 5. Let's say y is equal to 7x. So dy over dx would simply be 7, right? And similarly, if let's say y is equal to 12x, dy over dx would be 12. And if you want to know why it is just simply 12, if you want to know the logic behind it, let's delve into the logic. All right. Let's say let's I will I will show you the logic of this particular question. When y is equal to 12x, right? We know that if there is nothing here, there is 1, right? So let's say the 1 comes down, 12 is multiplied with 1 as per the previous models, and x 1 minus 1, all right, which is what? Which gives us what? 12x power 0. And anything raised to the power 0 is what? 1. So the answer eventually is 12, all right? So this is the logic behind it as per the previous modules, right? This is the logic. So whenever you encounter only x, so that would be 1. Let's say we have y is equal to x. You can just simply write it as dy over dx would be 1. All right. So this is the logic behind it. Okay. All right. Model number 4. Model number 4. Model number 4. What is the differential of a constant? So the differential of a constant is always 0. All right. Okay. So which means, let's say if we have y is equal to 5, dy over dx would be 0. Similarly, if we have y is equal to 7, whatever number, dy over dx would be 0, and so on and so forth. All right. So yeah, we can also write that differential of a constant is always 0. All right. And the logic of this is not required, but if you want to know it, it pretty much follows the same logic. Let me just show you an example. Let's say, let's use 7 as an example. So y is equal to 7. All right. So we know that it can be rewritten as 7, 1, right? It is multiplied with 1. And we know that 1 is what? Have x0. We can write 1 as x power 0. And now if we differentiate this, which is equivalent to this, we will get 0. All right, let's just differentiate it. Dy over dx, 7 multiplied by 0 is 0. And x power minus 1. 0 into x power minus 1 is what? 0. So this is why differential of a constant is always 0. All right, this is the logic. Even though it is not required, all you need to know is this. Okay. So moving on to model 5. Model number 5. All right. So y is equal to ax plus b power n. So the differential would be dy over dx, n would come down, ax plus b, n minus 1. Now the only difference is that this is multiplied with differential of the bracket, which is a, right? Differential of the bracket is what? A. Okay, so this would give us an ax plus b n minus 1. Okay, so let's do an example. Let's say we have y is equal to 5x minus 8 power 7. All right, so the differential would be 7, 5x minus 8, 7 minus 1, 6 into differential of the bracket, which is 5. All right, so 5 sevens are 35. 5x minus 8 power 6. This is our final answer. All right, so let's do another example. Let's say we have y is equal to under root 4x minus 3. D, let me just simplify it first, right? Y, it can be rewritten as y is equal to 4x minus 3, the whole thing, power 1 upon 2. So dy over dx would be 1 upon 2, 4x minus 3, 1 upon 2 minus 1, which is minus 1 upon 2, minus 1 upon 2, the differential of the bracket, which is 4, right? This cancels out. Dy over dx is 2 upon 4x minus 3, the whole thing under root. All right. So this is how it would look like. So moving on to model 6, which is pretty much the same model. All right. So model number 6. Model number 6. Whenever we have, let's say we have a function which is function fx, all right, and the whole thing power n. So the differential of this function would be n fx n minus 1 into differential of the bracket, all right. So this is essentially the same thing, but here we have, here the differential is the constant, and here we have a whole function, right? Let me give you an example to make things clear. Let me just write where fx could be any function, could be any function. All right. So let's say we have y is equal to under root 8x square minus 4x plus 7. All right. So we can write this as 8x square minus 4x plus 7, the whole thing power 1 upon 2. So dy over dx would be half 8x square minus 4x plus 7, 1 upon 2 minus 1, which is minus 1 upon 2, into differential of the bracket. All right, which would be a to the 16x minus 4. All right, so this could be rewritten as, so we can do one thing here. We can now take 2 common from here, right? Take the 2 common, right? So that this and this cancels out, and this can simply be written as 8x minus 2 upon, this would go into the denominator, which is 8x squared minus 4x plus 7, all right? And under root, right? Because this is minus 1 upon 2, which is under root. Even though even if you do not take 2 out, it would be completely, completely fine. But I just did it for the sake of simplification, all right? So moving on to our next model. Model number 7. Finding the gradient at a particular point. Finding the gradient at a particular point. So in order in order to find the gradient at a particular point, find the gradient at a particular point, we will first differentiate. We will first differentiate the given equation, differentiate the given equation, and then substitute the x coordinate, the x coordinate of the given point, of the given point in the differential to find the gradient. In the differential to find the gradient. All right. So let's say we have to find the gradient, find the gradient of the curve, find the gradient of the curve at of the curve y is equal to x cube minus 5x plus 7 at point 1 comma 3, right? So we will first differentiate. Okay, let's say y is equal to x cube minus 5x plus 7. We will first differentiate the equation. Dy over dx would be 3x square minus 5. Right now we will just simply insert this x coordinate into the differential equation, which would give us 3 1 square minus 5, which is minus 2. So this is the gradient of the curve at point 1 comma 3. Another example of this, let's say the question says find the gradient, find the gradient of the curve at the curve y is equal to under root 4x plus 1 at the point 2 comma 3. All right, so let's do this. Okay, so y is equal to under root 4x plus 1. We can rewrite this as 4x plus 1 power 1 upon 2. So if you differentiate it, you will get 1 upon 2 4x plus 1, 1 upon 2 minus 1, which is minus 1 upon 2 into differential of this bracket, which is 4. This and this cancels out, which leaves us with 2 4x plus 1 power minus 1 upon 2. All right, now if you insert this x coordinate, you will get the gradient at this point. All right, 2 4 2 plus 1 minus 1 upon 2. All right, so this is 9 minus 1 upon 2, which is equivalent to 2 upon 3. This is our answer. I hope this model is crystal clear. Okay, so model number 8. Moving on to model number 8. All right, model number 8. This model is the product rule, something I believe you have not studied in AS. Okay, so all right, when two functions are multiplied in such a manner that they cannot be converted that they cannot be converted into a single function, then in order to differentiate, then in order to differentiate, we apply the following rule. We apply the following rule, and the rule is as follows. Let's say we have two functions, ax plus b, cx plus d, in such a manner that they cannot be converted into a single function. So we will apply the following rule. Okay, we will take first function as a, not as a, but as u rather, right? U, and the second function is v. All right. Now u is ax plus b. It doesn't matter. The brackets don't matter, by the way. Yeah. And v is cx plus d. All right. Now what we will do, we will differentiate both functions separately. So u dash would be a and v dash would be c. Once you have done this, you will apply the following formula. Dy over dx is uv dash plus vu dash. All right. So this is what you need to remember. Okay. This is what you need to remember when you encounter two functions which cannot be converted into a single function. So you have to apply dy over dx is uv dash plus vu dash. Remember that. Okay. So let's do an example of this. All right. Let's say we have y is equal to x square under root 4x minus 5. All right. So this is u and this is v. So u is x square, u dash is 2x. All right. And v is 4x minus 5 power 1 upon 2. And v dash is 1 upon 2, 4x minus 5, 1 upon 2 minus 1 upon 2, minus 1, which is minus 1 upon 2, into differential of the bracket, which is 4. That leaves us with v dash is 2, 4x minus 5 power minus 1 upon 2, which is 2 upon 4x minus 5 under root. All right. So now we have u dash v dash. Now we will simply apply the formula, which is uv dash plus vu dash. All right, just simply apply this formula and you will get the answer. Okay, so dy over dx is u 2x and v dash is 2 upon 4x minus 5 uv dash plus vu dash. V is 4x minus 5 1 upon 2 plus vu dash and 2x. All right. My bad here. We used 2x. We used 2 dash here, right? We have to use u here, right? So u, 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 v dash plus v for v, u dash. Okay. So let me just move it. Wait. Okay. So yes. So that would give us 2x square upon under root 4x minus 5 plus 2x upon 4x minus 5. Sorry. Uh, my screen is not working. Wait. So yeah, it's okay now. So yeah, the uv dash plus vu dash, right? So that this would give us this. Okay. So now if you want to simplify this further, you can, but this should do it. All right. If you can simplify it further, you can. That's right. If the question asks you to find the gradient at this point, I don't think so there's any need to simplify it further. But if the question asks you to simplify, give your answer in the simplest form, I think you should. All right. So similarly, now let's move on to model number 9. I hope this model is clear. So model number 9. Now, what if two functions are divided in such a manner? Okay. Right. Model number 9. Okay. So then we apply what we call quotient rule. Okay. quotient rule. Okay, so if two functions are divided in such a manner that they cannot be converted that they cannot be converted into a single function into a single function, then in order to differentiate, then in order to differentiate, we will apply the quotient rule. We will apply the quotient rule as follows. Okay, so let's say we have y is equal to ax plus b upon cx plus d. All right, so this would be u and this would be v, and we will apply the following formula. Dy over dx is vu dash minus uv dash upon v square. So this is the formula that you need to remember when two functions are being divided in such a manner that they cannot be converted into a single function. All right, so you need to remember this. Now let's apply it. Okay, so let's say we have y is equal to 4x minus 3 upon 5x plus 1. All right, this is u, this is v, and u is equal to 4x minus 3, u dash is equal to 4, v is equal to 5x plus 1, v dash is equal to 5. All right, so now just apply this. Dy over dx is equal to vu dash minus uv dash upon v square. V is 5x plus 1, u dash is 4, vu dash minus uv dash, u is 4x minus 3, right? And minus uv dash, v dash is 5 upon v square, 5x plus 1 square. Okay, so this would give us, if we multiply 5 for the 20, x 4 ones are 4, minus 5 into 4, which is minus 20x, right? Minus and minus plus 5x is a 15 plus 15. All right, this and this cancels out, and we are left with 5x plus 1 square in the denominator, and plus 4 plus 15 gives us 19, and 5x plus 1 square. This is the answer. Okay. So model number 10. Model number 10. Stationary point. Stationary point. All right. So stationary point is also called turning point, and to find the turning point and to find the turning point turning point we will equate we will equate dy over dx with 0. All right. And then what we will do, substitute the x coordinate of the turning point, x coordinate of the turning point in the equation to obtain the y coordinate of the turning point. All right. So let's do an example. Let's say we have a question which says find the stationary point of the curve y is equal to 3x square minus 12x plus 7. All right, so we have to find the stationary point of this curve. So we will just differentiate. When we differentiate, we get 3 to the 6, 6x minus 12. And now equate the differential to 0. All right. So 6x is 12 and x is 12 upon 6, which is 2. X is 2. Now we'll substitute this back into the equation to find y. All right. So y is 3, 2 square minus 12x2 plus 7. So y is 12 minus 12 into 2, which is 24. 12 minus 24 plus 7. So y is 12 minus 24 plus 7. Y is minus. Sorry for that. Y is minus 5. All right. So we have the stationary point 2 comma minus 5. This is the answer. All right. Model number 11. Nature of the turning point. Nature of the turning point. All right. So once we have found the x coordinate of the turning point, it is important to identify, it is important to identify the nature of the turning point. The nature of the turning point, whether it is maximum, whether it is maximum or minimum. All right. And in order to do this, in order to do so, we will double differentiate the equation. We will double differentiate the equation, or in other words, or in other words, we will calculate t square y dx square or f double dash x or y double dash. All right. And if d square y upon dx square is greater than 0, then this is minimum turning point. All right. If d square y upon dx square is less than 0, then this is maximum turning point. And if d square y upon dx square is equal to 0, then it might be a point of inflection. And what is a point of inflection? For that, we have to wait till model 12. All right. So let's do an example of this first. Okay. So let's say the question says to find the stationary point, at find the stationary point of the curve y is equal to x cube minus 5x square plus 8x minus 1, and determine its nature. All right. So first we have to find dy over dx. So dy over dx would be 3x square minus 5x plus 8. All right. Sorry, we have to multiply this as well, right? X square minus 10x plus 8. All right. So now we will simply apply model number 10 to calculate the stationary point first. So let's say 3x square minus 10x plus 8. We will equate it to 0, and this will give us 2 points of x. All right. So yeah, this is a quadratic equation. So we have to solve this. 3x square minus 6x minus 4x is minus 10x plus 8 is equal to 0, and 3x to the 3 x minus 6 minus x minus 2, x minus 2 minus 4 minus minus plus x minus plus minus 4 to the 8 is equal to 0. So 3x minus 4 and x minus 2 is equal to 0. And we have x is equal to 3x minus 4 is equal to 0. And 3x is equal to 4x is equal to 4 upon 3. This is our first point. And x is equal to 2, right? We have 2x. Now we have 2. Now notice that since this is a cubic equation, right? So we have 2 turning points. All right. So, okay. So now we have to substitute these turning points in the equation to calculate y. When x is equal to 4 upon 3, right? So y is 4 upon 3 cube minus 5, 4 upon 3 square plus 8, 4 upon 3 minus 1, and y is equal to 85 upon 27 if you solve this using a calculator. And now, so first point is, so we have, let me just write it down. So we have one stationary point equivalent to 4 upon 3. One point is 4 upon 3 and 85 upon 27. This is one point. Okay. So now when x is equal to 2, all right, so y would be 2 cube minus 5, 2 square plus 8, 2 minus 1. This would give us 3. All right. So 2 stationary points are 4 upon 3, 85 upon 27, and 2, 3 respectively. All right. So we have done the first part and we have found the stationary point of the curve. And now we have to determine its nature. All right. So notice that dy over dx was, notice that dy over dx is 3x square minus 10x plus 8. 3x square minus 10x plus 8, right? 3x square minus 10x plus 8. Now we have to double differentiate it. Okay. So d square y upon dx square would be 6x minus 10. All right. So now just simply insert this x value here. 6, 4 upon 3 minus 10. All right. So 6, 8 minus 10. This would give us minus 2. All right. This means since d square y upon dx square is less than 0, this means that this point is therefore a maximum point. All right. This is a maximum point. Okay. Now let's apply d square y upon dx square here. 6x minus 10. All right. 6x2 minus 10. 12 minus 10. This gives us 2. Now notice that d square y upon dx square is greater than 0. All right. Therefore, this point is a minimum point. All right. So this point is maximum and this is minimum. Okay. So model number 12. Now let's move on to model number 12. The point of inflection. Model number 12. Point of inflection. All right. Point of inflection exists when d square y upon dx square is equal to 0. All right. There is a possibility that it might be a point of inflection. Now let's study it. Okay. So let's write if the function is such that d square y upon dx square is equal to 0. All right. We need to check. We need to check whether point of inflection exists or not. Point of inflection exists or not. All right. This is because when d square y upon dx square is equal to 0, it can either result in a maximum point, minimum point, or point of inflection. A point of inflection. Hence, in order to identify, hence, in order to identify, we will apply the following steps. We will apply the following steps. All right. Step number 1. Equate dy over dx. Equate dy over dx with 0 and calculate the stationary point. Calculate the stationary point. All right. Step number 2. Step number 2. Find d square y upon dx square and substitute the x coordinate of the stationary point in it to observe Yeah, sorry for that. You need to observe that that the result is 0. That is d square y upon dx square is equal to 0. All right. Then apply step number 3. Step number 3. Deduct 0.1. Deduct 0.1 from x coordinate of the stationary point. Stationary point and substitute it in dy over dx. All right. Step number 4. Add 0.1. Add 0.1 to x coordinate. Add 0.1 to x coordinate of the stationary point. Stationary point. And substitute it in dy over dx. Step number 5. Step number 5. If answer of step 3 if answer of step 3 is positive, while the answer of step 4 is negative, right? This means that the turning point is the maximum turning point, right? It is an indication that it is an indication that the turning point is the maximum turning point, right? So let's say x is equal to 5, right? And x is equal to 4.9 and x is equal to 5.1. We deducted 0.1 from the turning point and added 0.1 to the turning point. All right, so dy over dx, let's say it's positive. At x is equal to 5, it is 0, like this. And dy over dx at x is equal to 4.9 is positive. So it would be like this. And at 5.1, it is negative. It would be like this. Positive, negative. Now, this is an indication that the curve goes like this. All right. And this is what? And this is a maximum turning point. All right. Now, similarly, let's say step number 6 says if answer of step 3, if answer of step 3 is negative, while answer of step 4 is positive, while answer of step 4 is positive. It is an indication that the turning point is a minimum turning point. It is an indication that the turning point is a minimum turning point. So it would go something like this. Let's say one answer is negative, right? X is equal to 5, and other answer is positive. So it would give us a minimum turning point, right? This would be a minimum turning point. All right. So this would be a lot clearer when we do an example. All right. So let's say if signs of step 3 and step 4 are same, that is either both are positive or both are negative, then it is an indication that the point of inflection exists. All right. So let's just write it down. If signs of step 3, if signs of step 3 and step 4 are same, all right, that is either both are positive, either both are positive or negative, then it is an indication, then it is an indication that point of inflection exists. That point of inflection exists. Let's say we have both our step 3 and step 4 are positive. All right, this is 0 and this is positive, right? Positive. So the curve would go like this, and this is the point of inflection. Let's say both are negative, right? The curve would go like this. All right. And this is the point of inflection. All right. So what we learned is that when d square y upon dx square, that is the double differential, is equal to 0, then there are three possibilities. First possibility is that it could either be a maximum curve. Second possibility is that it could be a minimum curve. And the third possibility is that it could be a point of inflection like this. All you have to do is follow the above steps and you will land on the correct answer. All right. So just stick to these steps and inshallah you will be able to solve it correctly. Now let's do a question to make things clear. Okay. So given that the equation is such that y is equal to x cube minus 3x square plus 3x plus 5. Calculate the stationary point. Calculate the stationary point and determine determine its nature. All right. So y is equal to 2x cubed minus 3x squared plus 3x plus 5. So dy over dx would be 3x squared minus 6x plus 3. Equate it with 0 to get the stationary point. If we simplify it, we'll get x squared, taking the 3 common, we'll get x squared minus 2x plus 1 is equal to 0. So if we solve this quadratic equation, right, we will get x minus 1 minus 1, x minus 1 is equal to 0. I have skipped a step, but you have to show steps in the exam. X is equal to 1, x is equal to 1. All right. So the stationary point is x is equal to 1. Okay. The x coordinate of the stationary point. So the y coordinate would be y is equal to 1 cube minus 3, 1 square plus 3, 1 plus 5. Y is 6. So we have the stationary point or turning point 1, comma 6. All right. So now d square y over dx square. D square y over dx square would be 6x, since this is dy over dx, 6x minus 6. All right. So let's just put the x coordinate here, right? T square y upon tx square is equal to 6, 1 minus 6. All right. So t square y upon tx square is 6 minus 6, which is 0. All right. So now we have to check whether it is a maximum point, minimum point, or the point of inflection. Let me just copy it. We don't have space here. Let me just copy it to the next page. It was not copied. Let me just do it again. Okay. Okay. So the stationary point was 1. All right. We know the stationary point was 1. If we subtract 0.1 from here, we get 0.9. And if we add 0.1 here, we get 1.1. All right. So we would uh, put this in dy over dx. Okay. That would give us dy over dx is 3x square minus 6x plus 3. 3 let's just put it in this simplified version. Okay. which is x square minus 2x plus 1. So we have 0.9 square minus 2, 0.9 plus 1, okay, and which is dy over dx is 0.03. Notice that this is positive. All right. Now, if we put 1.1 in dy over dx, we get 1.1 square minus 2, 1.1 plus 1, 1. So we get dy over dx, which is the same, plus 0.03. So this would be something like this, right? This is the stationary point. This is the stationary point, right? So this would be plus 0.03 plus 0.03, and the curve would be something like this. So yeah, when both are positive, we know that point of inflection exists. There's no need to draw this. We can just simply write both are positive, both both are positive, thus point of inflection exists. All right. So this is how we do such type of questions. Okay. Moving on.